All right, here we go. This is section 11.7, and you will need to grab your calculator and participate because there are a lot of calculations here. Not hard, but there are lots of calculations. So you need to make sure you have a calculator. You need to make sure you're ready to participate in it, whether it's, verbally or at least following along, because I'm going to need people to throw out numbers. I can do a lot of this in my head, but not all of it, okay? So let's take a look at how this works, all right? It's not hard, but lots of multiplication and understanding how one probability might impact another, okay? So what's happening now is that we're doing essentially multiple probabilities in a row. So for example, we spin this once. What's the probability of it landing on something? Figure that out. Then you spin it again. What's the probability of it landing on something else? What's the total probability? Or if we spin it 3 times and 4 times. Does that make sense? That's what we're doing here. So let's take a look. It says, if the pointer is spun twice, find the probability that will land on blue and then purple. This is not hard at all. So in this problem, you need to figure out the probability of getting blue, okay? Then you're going to figure out the probability of getting purple. Does that make sense, guys? Okay? Now, what are we going to do with it? We're going to add, subtract, multiply, divide. What do you think? Well, we'll find out, shall we? Okay, so it's better for you guys to go figure this out. We'll decide what we're going to do with that in a moment. Okay, I don't want to just fully give it to you, but here we go. What's the probability if we spin it once, the first time, of getting a blue? What would it be?
3 out of 6.
3 out of 6 or 1/2. Let's use 1/2, the simplified version, shall we? What's the probability of getting purple on the second spin? 1/3, because there's 2 out of 6, or 1/3. Now, why don't we multiply them and see if that's the right answer? What's 1/2 times 1/3? 1/6. And there you go. So you multiply.
That's it? That's the answer?
That's the answer. So the probability of getting a blue on the first spin, then a purple on the second, is the product of the probability of getting a blue and a probability of getting a purple. Does that make sense, guys? That's it. I'm telling you, it's not bad. It's like this the whole section. All right, let's take a look at this next one. Okay, find the probability that if we spin it 3 times, the first time we get green, then we get yellow, then we get purple. So what are we going to need to do? Probability of getting green. Oops, mix that. So that's going to be the probability of getting green. What's the operation? Multiply. Then probability of getting what? Yellow. Multiply. Probability of getting what? Purple.
Okay, can I ask a question? Just really quick. On this one, compared to some of the ones we did yesterday with the spinner, is it those words like or, and then that make a difference?
Yes, yes, but
which operation to use?
you'll see in a moment.
Okay.
Yes, so just follow each one, and what you'll do is you'll see how they are semi-dependent on each other. And if you're in doubt, I have the lecture up, so you can watch the lecture,
Okay.
right? So I recorded the lecture. There's a lecture up to watch 11.6. Okay. If you're ever unsure, you need to come back to it to prep for your test. So what's the probability of getting a green? In this
2
one.
out of 8.
1/4.
2 out of 8 or 1/4, exactly. 2 out of 8 total. There's not 6 on this one, 2 out of 8. And it is helpful to simplify first because it makes your multiplication easier. All right, how about probability of getting a yellow? 1/4 as well. There's only 2 yellows, 1/4. How about probability of getting a purple? 1/8. There's only 1 purple. Does that make sense, everybody? Okay, and so your answer is the product of those. 1 times 1 times 1 is 1 for the numerator. 4 times 4 is 16. 16 times 8 is
128.
what was it?
128.
128. Okay, good. There you go. Does that make sense, everybody? I'll type it in just to make sure so you guys can see. Got it? All right. So it doesn't have to be 2 times or 3 times. It could be multiple times. You just find the individual probabilities. All right. Now, let's do this next one. If the spinner is spun 3 times, find the probability that it will land on yellow every time. That means how many probabilities are we going to need? 3 of all yellow. Does that make sense, everybody? So you want the probability of yellow, and then another yellow, and then another yellow. Is this any more difficult than the previous ones? No. What's the probability of getting a yellow? 1/4. Times another, 1/4. Times another, 1/4. Does that make sense, guys? Okay, and so the answer would be what? 1/64. Okay, everybody got that? We okay? Is that video still going?
Yes.
Perfect, thank you. Let's go to this next one, all right? This time, we're dealing with rolling a die, okay? We're dealing with rolling a die, and it says, how many times are we going to roll it? Twice. So you know you're going to have 2 over here that you need to find, 2 probabilities. Find the probability of rolling a 2 the first time. All right, so we already know what we need to do. Probability of getting a 2 times, let's see, a 5 the second time. And that's it, because we're only rolling it twice. Here it is. Find the probability of rolling a 2 the first time and a 5 second. What's the probability of rolling a 2? 1/6. There's only, it's even on all sides. Each side has a unique number. Then from there, what's the probability of rolling a 5? 1/6 as well. So the answer? No, careful, multiply.
Oh, 36.
Yeah. Can't add the denominators. Be careful with that. 1 out of 36. Okay, let's keep going. All right, so we're going to roll this die twice again in this next problem. Find the probability of rolling an even number the first time, and then rolling a number greater than 1 the second. All right, so let's take a look here. So our setup is the probability of rolling an even the first time, and then the probability of rolling a number greater than 1 on the second. We're only rolling it twice. We could roll it multiple times, more than just 2, but this one just happens to be twice. So how many ways can we roll an even number on a 6-sided die? 3 out of 6 or 1/2. Good job. Always simplify if you can to save yourself work. How many ways can we roll a number greater than 1? 5. Basically everything besides 1. You can't simplify that, right? So the answer?
5/12.
Exactly, 5/12. Done. Does that make sense, guys? This is as easy as it seems. Okay. Now we go to a deck of cards. Same concept, different scenario. 52 card deck, just like we've been working on for this whole section. Okay, so important note here, you're going to draw a card and then you're going to put it back in. And that's why all of these that we've been doing are mutually exclusive. And recall that from our last class, well, if you watch the lecture, mutually exclusive means that what happens on the first doesn't impact the second or any successive ones. Meaning that we spin it, that spin doesn't impact, technically, the other ones. Okay? And so that's why they say the card is then put back in. We're not dealing with fewer cards. But later in this section, it's not hard, we will deal with not mutually exclusive scenarios where if you pull a card and you leave that out, then you go for your next pull, what happens? It's not hard, we'll get to that. So let's take a look. That's why they say the card is replaced, to tell you that you're back to 52 after you select one. Does that make sense, guys? Okay, so here we go. The card is replaced and the deck shuffled, and you draw again. So how many times are we drawing? Twice. Find the probability of drawing a 6 on the first time and a club on the second. Okay, so we need to figure out the probability of getting a 6 and a probability of getting, I'm not gonna draw a picture because I'm terrible at them, a club, right everybody? So, first, let's just focus on the 6. How many 6s are there in a deck? 4 out of 52. If we simplify 4 out of 52, what is that? 1 over 13. Okay? So 4 out of 52. Remember I said a moment ago, always simplify if you can. It's going to make your work easier. 4 out of 52 simplifies to 1 over 13. You can check it yourself. Now, let's go take a look at the clubs. We put that card back in, which means we start fresh with 52. Okay? Later, it's going to change a little bit when we do non-mutually exclusive situations. So, how many clubs are there in a deck? 13 out of 52, because we put that card back, which is really the same as reduced 1/4. Good job. Love the participation. I have to have that, otherwise we won't get these numbers. And so, we're only drawing twice, which is why you only see 2 probabilities here. And this is 1 over what? 52. There it is. Does that make sense, everybody? And it really is this simple throughout the section. Okay? All right, let's take a look at this next one. Another card. So, keyword, phrase, card is replaced, right? Okay, find the probability of drawing a jack each time. How many times are we drawing? Twice, if you read the problem. So, this is kind of like our yellow spinner, except a different scenario. Probability of a jack, and then a probability of another jack. Everybody agree? So, how many jacks are there in a deck? 4 out of 52, which reduces to 1 over 13. Because we put the jack back in, or the card back in, it doesn't necessarily have to be a jack, but whatever card we pulled the first time, we put it back in and reshuffle. What's the probability of getting a jack again? Same 1 over 13. And so the probability is 1 out of 169. Good job. Well done. It's that easy. No big deal. Okay, moving along. All right. Now we move to a coin flipping scenario, which means that there's how many possibilities? 2, right? So just, let's take a look. What is the probability of getting 3 heads in a row when flipping a coin? So in other words, we flip a coin, we're looking for a probability of getting a heads, another probability of getting a heads, another probability of getting a heads, which is what on each of them? 1/2, right? It's that simple. Which is a probability of 1/8. Does that make sense, everybody? Okay, three coin flips. Doesn't always have to be 2 or 3 or 4 or 5, whatever it happens to be. So 1/8. All right, let's move on. All right, let's do this one. It's a mix. A coin is tossed, and then a die is rolled. Is it the same denominator for each of these probabilities? No. One is going to be a denominator of, and the other one's going to be a denominator of 6. Does that make anything more difficult? No. It's easy. Okay? Find the probability of getting a head. Okay? Because that's the coin toss. And then a number greater than 1. So all you got to do, again, because they're mutually exclusive, they're separate from each other, is find the probability of getting a head. What's that? 1/2. And what's the probability of getting a number greater than 1 on your, then you roll your die? 5 over 6. Exactly. For a total probability of 5 over 12. That's it. Does that make sense, guys? Okay, no big deal at all. Okay, let's keep going. All right, next. The probability that a certain state will be hit by a major tornado in any single year is 1 out of 15. Use this information to answer the question below. Part A. What is the probability that the state will be hit by a major tornado 2 years in a row? So what I'm going to do here is I'm going to say probability of getting a tornado and then probability of getting another tornado because it's first year and second year. Everybody agree? Does that make sense, guys? Now, what's the probability of getting a tornado? 1 out of 15. What's the probability of getting it the second year? Another 1 out of 15. It doesn't change. The probability is still the same. Or according to them, right? So therefore, what's the fraction? 1 out of what? 225. Now, let's pause for a moment here because things have changed just a bit. In this problem, they don't want the fraction. They want to round to 5 decimal places. So you're going to actually need to do 1 divided by 225 and tell me round it to 5 decimals. What is that?
0.00444.
Okay, 0.00444. Let's just double check that. And there it is. Does that make sense, guys? So you need to pay attention and make sure that you read whether they want a decimal rounding. It might be, in later problems, it'll be 3 decimal places, 5 decimal places like this one, or a fraction. Does that make sense? Okay, good, wonderful. Now, part B, 3 consecutive years. What's the only thing you would change? You do another 1 over 15. You multiply by another 1 over 15 and round to 5 decimal places on your answer. Does that make sense, guys? And then the next part is, I think, 5 consecutive years. Does that make sense? So I'm going to skip this. I don't want to keep going on it. Let's move on. Are we okay? All right. Okay, number 11. Okay, a little graph here. Let's take a look here. All right. So it says the graph shows how students at a local college rate their study skills. Assume that the selections are independent events. Independent events, not related. Okay, so one probability is not tied into the next one. Very important that that's distinguished because, like I said again in a moment here, they are going to be potentially tied together. Okay, if 3 students are selected at random, that immediately tells you you're going to have 3 different probabilities. Does that make sense, guys? It's not going to go 2 like in the tornadoes. It's going to go 3, or the first tornado did. Find the probability that all 3 rate their study habits as poor. Okay, so you select 3 students. I'm going to continue it over here. Student 1, student 2, student 3. Everybody agree? Right? Find the probability that they all rate it as poor. Now, unlike before, they give you it as a percent. Well, that's not a big deal. Just take the percent and convert it to a decimal. And now you have something like this. Does that make sense? What's 6% as a decimal? 0.06. Well, since they say all 3 rated as poor, you're going to use the same one, right? Now, if they said the first one rates as poor, the second one rates as excellent, the third one rates as good, you're going to use those decimals for those. Does that make sense, guys? But for this problem, since they happen to say they're all rating as poor, then you'll use the 0.06 for all 3. Does that make sense? Okay? And again, say it one more time. If they say, okay, find the probability that all the 3 students, the first student rates as poor, the second student rates as fair, the third student rates as good, you'll use the respective decimals for those. But since this one is that, you just use that. Anybody got an answer for that?
0.000216.
And let's see here, round to 5 decimal places, so 0.00022, right? Okay, so it's going to be there. Does that make sense? All right, let's type it in, make sure we got it, and we'll move along. 0.00022. Done. Does that make sense, guys? Perfect. Rolling along. Okay. Okay. Now to a box of donuts. Elizabeth bought a box of donuts to share. There are 24 donuts. Boom. They already tell you how many donuts you're working out of. You're working out of 24 or 24. 24 is your denominator. Does that make sense, guys? Okay. All identical in size, shape, and color. 5 are jelly filled, 9 are lemon filled, and 10 are custard filled. Okay, does that equal 24? 5 plus 9 is 14, 14 plus 10, there's the 24. Done, okay? You randomly select one donut, eat it, and select another donut. Find the probability of selecting 2 custard-filled donuts in a row. Okay, you already see where this is going, don't you?
Yep.
Are we changing directions a little bit?
Yep.
Yeah. This problem is not, I'm going to say not mutually exclusive. Everybody agree? Because once you eat one of the donuts, it affects the total denominator. You got it. Let's go do one at a time. First and foremost, what's the probability on the first pull of getting a custard?
5 out of 12.
5 out of 12 because it's originally 10 out of 24. Everybody agree? There are 10 custard-filled donuts, a total of 24. When we reduce that by 2, that's 5 over 12. Everybody agree? Okay. Now, you just ate that donut, whatever donut you got. Do we still have 24 donuts? No, because you don't throw it back up and put it back in the batch. No, you're done. You're eating it. It's getting digested, okay? So we are down to 23 donuts. It doesn't matter what they are. You're down to 23. Now, okay, we pulled a custard-filled one, which means how many custard-filled are left? 9 out of 23, exactly. Because what they asked for is that what's the probability of getting a custard on the first? 5 out of 12. So they're assuming that we actually got a custard, so that means there's one less custard and and as a result, one less total donut in the batch. Meaning that there are only 9 custard-filled donuts left and 23 total donuts left. And there it is. Now you understand why the not mutually exclusive must be handled slightly differently from the mutually exclusive. Okay? And so if you can simplify, you should. And let me show you. Cross cancel here. You should know how to do it if you're in this class. Divide everything by 3 here in the diagonal. 9 divided by 3 is 3. 12 divided by 3 is 4. Now multiply across. What's 5 times 3? 15. What's 4 times 23? 92. Okay? And
I'm so glad that you did that. I should know that, but I totally forgot about
the
it.
cross cancellation. Well, we'll have some more examples of it. That way you guys are in good shape.
I mean, mine was a little bit different, so I couldn't do that.
Yeah.
But had you
Always
done that,
look
I wouldn't have
for,
done
yeah,
it.
always look for the cross cancellation and practice with it, okay? And we have, 14, 15 more problems to go. All right, so we're good. All right, let's go do another donut problem. All right, so it says Elizabeth brought a box of donuts to share. In this case, we still have 24 of them. Okay, 2 are jelly filled, 7 are lemon, and 15 are custard. Okay, you randomly select one donut and you eat it. That's very important. Boom, right there. That part tells you you're not dealing with mutually, you're dealing with a not mutually, because now you're taking one out and it's impacting the next selection. Okay? All right, find the probability of selecting a lemon-filled donut. All right, so probability of lemon, okay, followed by a custard. Okay, all right, sounds good. Okay, let's take a look here. What's the probability of getting lemon?
7 out of 24.
7 out of 24, which cannot be simplified, so I'm going to write 7 out of 24. What's the probability of getting a custard?
15 out of 23.
15 out of 23. Let's pause for a moment and understand what's going on here. The first one is lemon filled. You pulled a lemon. You had 7 chances of doing it. You actually got the lemon one, and you ate it, which means that there are only 23 donuts left. Does that make sense? But there are a total of 15. There's still 15 custards, aren't there? And so, there are 15 out of 23. Does that make sense, guys? Now, don't go straight multiplying across. Cancel if you can. 7 and 23, nothing in common. But 15 and 24 can both be divided by 3. 15 divided by 3 is 5. 24 divided by 3 is 8. Now go multiply across. 7 times 5 is 35. 8 times 23, 24, 184?
Yes.
Okay. And there it is. I don't believe that can be simplified anymore. Nope. And the thing is that when you cross cancel early on in the problem like that, you save a lot of hard simplification at the very end. Okay? And there it is. Let's move on. All right. Same concept, but now we deal with politicians. Yeah. Suppose that 2 group members are randomly selected from our 6 Democrats, 5 Republicans, and 4 Independents. What are you going to have to do because they didn't tell you the total number of donuts?
Add one up.
I said donuts because.
Yeah.
So we do need to find out the total, right? Because they don't give you the total number of them like they did in the
15.
donuts. So there are 15 total. Does that make sense, everybody? Okay. So that's your starting denominator. Is that your secondary denominators? No, not necessarily. So, all right. If you select a group member, can you put the group member back in? No. You've already taken one out of the pool of politicians. You cannot put that one back. You've already assigned that person to something. So, all right. Find the probability of selecting 2 Democrats. Okay, so basically we're going 2 Democrats in a row. Right? And so, what is the probability of getting a Democrat the first time?
2 out of 5.
Yes, so 6 out of 15, 6 Democrats out of 15, or if we reduce it by a factor of 3, 2 out of 5. That's how we get 2 out of 5. 6 divided by 3 is 2, 15 divided by 3 is 5. That's how we get it. Now, do we still have the same amount of total politicians? No, we've been reduced by 1. Do we have the same amount of Democrats? No, we're reduced by 1. So the second time we select, what is our probability?
5 out of 4.
5 out of 14 the second time. Because we have 1 less Democrat because we're pulling Democrats, and we have 1 less total politician. That can't be reduced, so we'll just write in 5 out of 14. Does that make sense, everybody? And again, always look to cancel. This problem, we can actually cancel in both. 2 and 14 can be canceled. 2 becomes 1. 14 becomes 7 because they're both divisible by 2. Is it still going?
Yeah.
Excellent, thank you. 5 and 5 can cancel. They're both divisible by 5, which makes a 1. 1 times 1 is 1. 1 times 7 is 7. There it is. Does that make sense, everybody? Any questions about that at all? Starting to get the hang of it? Really isn't bad.
Yeah.
Last section is hard. Much harder. All right, let's keep going. Same concept here, still dealing with politicians. Consider a political discussion group. There they are. Are there 15? 12? No, there aren't. There are how many?
18.
18. Yeah, so there are 18 this time. Suppose that 2 group members are randomly selected in succession. So we're only doing 2 this time, again. Find the probability of selecting a Republican and then a Democrat. Okay, so Republican, then a Democrat. Okay, so here we go. What's the probability of getting a Republican?
4 out of 19.
Yeah, so 8 out of 18 to start. If we divide that by 2, it'd be 4 out of 9, right? So in our first poll, there are 8 total Republicans that we can get out of the total of the full 18. However, we've just taken one out of the pool, haven't we? Right? Out of the pool politicians. But this time we only need a Democrat, right? So how many Democrats do we have to get? 4 out of 17, because we're one less politician. That can't be reduced, so we'll just put that right there. Does that make sense, everybody? Okay, can anything be canceled in this one? No, nothing can be canceled. Therefore, we just multiply straight across. So that's 16 over 153. Excellent. All right. Everybody got that? Okay. All right, this one's important, even though it just looks like another one of these, the politician ones. It's not quite the same, but let's correct the total first. 8 and 6, 14, there's 16 total in our pool of politicians, or sample. Suppose that 2 group members, we're still dealing with 2, find the probability of selecting no Democrats. This is a new one, but it's not any different, so I'm going to come back to the top, erase this one. Find the probability of selecting no Democrats out of your 2 polls. That means that, what can you select? Exactly, Republicans and independents times another, Republicans and independents. That's really what you're looking for, isn't it? Does that make sense, guys? Mm-hmm. So, is it difficult? No. It just means you got to look at it slightly differently. So, first and foremost, first poll. How many ways, since we don't want any Democrats, can we get Republicans and independents? What is that?
Okay, what are you doing, the first one?
First one.
The very first setup? So it's what, 10 out of how many?
No, not 10 though.
Well,
8
8
over 16.
over 16, yeah, exactly. Be careful. So,
What?
we don't want Democrats. There are 8.
No Democrats. Okay.
There are 8 Democrats. So
Sorry.
we want the Republicans and the independents. That's 8 out of the 16 that are not Democrats. Does that make sense? Okay, good. Which is really 1/2. Now, the second time around, we've taken one person out, haven't we? Meaning that how many do we have to choose from? 7 out of 15. If one of these got pulled, that means you have one less. So you have 7 out of 15 total. That can't be reduced, so there it is. And nothing can be canceled, so that's 7 out of 30 as your answer. Does that make sense, guys? Okay. A little bit tricky, but is it really that hard? No. All right. Okay, on to juice. Okay. Let's take a look at this one. So I'm going to erase this. Erase that. Okay. So it says an ice chest contains 7 cans of apple juice, 5 cans of grape juice, 7 cans of orange juice, and 5 cans of mango juice. Stop right there. What do we need to do? Find the total. 7, 5, 12, 12, 19, and 24, right? 24 total cans. Key piece of information. All right, you're going to reach into the container and randomly select 3 cans in succession. You aren't putting them back in, which is why it's not a mutually exclusive scenario. We're not here. We are in a not mutually exclusive, okay? Each pull impacts the success of the pull. So find the probability of selecting 3 cans of mango. So we're looking for 3 mangoes in a row. Mango, mango, and another mango. Everybody agree? Okay. So first and foremost, first pull. What's our chances or probability of getting a mango? 5 out of 24. Second pull, we've pulled a mango, meaning that we have how many mangoes left?
4
Out of 23. Third pull, we pulled a mango, so we have 3 out of 22. Does that make sense, everybody? None of those could be simplified. So therefore, now let's go take a look. If we can cancel, we should. Let me help you cancel and show you how to cancel with 3. because most of you probably aren't familiar with that. You can only do one at a time. You can't do this divided by 2 and this divided by 2. You can only do a pair at a time. So I would do these two, 4 and 24. 4 would be divisible by 4, which is 1. 24 divided by 4 is 6. If you can find another in any you can even jump around if you want to. So 22 and 5, no. 6 and 3, yes. The 6 and the 3, as long as it's diagonal, you're okay. You can't go straight across. 6 and the 3, 6 and 3 are both divisible by 3. 6 becomes 2, 3 becomes 1. Keep looking. 5, 23, 2, anything up there? No. 22 and 5, 23 and 5, nothing else can cancel. So now multiply straight across. 5 times 1 times 1 is 5. 2 times 23, and real quick, you can't cancel 2 and 22 because they're on the same row. You have to do diagonally. 2 times 23 is 46. 46 times 22, need your help.
1012.
1012. Perfect, thank you. And that obviously can't be simplified, so that's your answer. 5 out of 1012. Does that make sense? All right, fantastic. I don't want to do number 18. We're good. That's on you. We've done plenty of examples on that. Let's move on. Okay. So I'm going to erase this right here, and I'll erase this. I'll erase down here. Okay. All right. Let's take a look at this next problem. Nothing crazy. Same stuff. If you can't see it, there are numbers on each of these. Okay, and colors, obviously. So it says the number discs shown are placed in a box, and one disc is selected at random. Find the probability of selecting a 5 given that a green disc is selected. This is actually super, super easy. It actually is easier than what we've been doing. Now, the key that you have to see is that given a green disc is selected, that's actually what needs to precede your selection. Because once they say a green disc is selected, you only have what to choose from? 4. Does that make sense? So your probability is actually out of 4. Does that make sense, guys? You don't have to factor in all 8. That's key. Now back up and find the probability of selecting a 5. So you only look at your greens. How many 5s are there in the greens? 1. That's it. Does that make sense, guys? So that's known as conditional. Because once this has happened, you've selected a green, then figure out what the probability of selecting
That's just it? It's 1 out of 4, done?
Yeah, you're it. That's it. Done. Okay, does that make sense? Okay, it really is that easy. Okay, you just have, oops, not 14, sorry. Make sense, guys? Okay, all right, let's keep going. Same concept, different problem. And so hopefully you guys can see the numbers. These are 1, 2, 3, 4, 5, 6, 7, 8. All right, so they say probability of selecting an odd number given that blue disc is selected. So you want to select an odd, but you first have to take into account that a blue has been selected, meaning that your probability is out of 4 as well. You don't care about the greens because that's not what they first specified. You've already pulled a blue, meaning that your odds have gotten better, right? So now, odd number. How many odds are in there?
1.
There's only 1 because it's 1, 2, 6, and 8. 2, 6, 8 are all even. So this one happens to be 1 out of 4 again. All right, there you go. All right, another one. Okay, same concept here. Find the probability of selecting a blue disc given that an even number is selected. So they reverse it this time, right? They don't pull a color, they pulled numbers. So we want the probability of getting a blue given that even numbers have been selected. Well, that means what are we taking? We've got this one, right? This one, and this one. Everybody agree? That's in our sample. So we're out of what? 4. They just happen to be mixed because it wasn't about the colors at first. It was about the numbers. So you've already pulled all the evens. What's the probability of getting blue? 2 out of the 4 even numbers, or 1/2. Okay. There it is. I'm going to leave this for you. Okay? All you to do. Next. Okay. All right, let's take a look at this one. So this is going to help us close out this section, these tables, and let's take a look at what we've got. So, let me move my... All right. So we have this table. It says if one person is selected from the population, find the probability that the person is not married. Okay, so let's take a look at this. You first, just like all of our previous problems, you needed to know the total, right? There it is. So you know your answer is going to be out of 210. Everybody agree?
Sir, yes, sir.
So what's the probability that a person is not married? Well, let's go over here. Never married is what? 51.4. So there it is. Do that division. Let's round to 3 decimal places.
So they don't mean like.
No, they
widow,
said not
divorced,
married,
it just
but they
says-
say not married. Doesn't
Yeah.
mean you have to be never married, so you could have widowed and divorced to that. Because
that's
they
a good.
said
That's
never married, they don't say probability the person has
That's a
never
good
married,
point.
Oh,
but
that's
is
really good.
not
Good
married.
catch.
How about let's do this.
Present
Let's
tense,
throw
bro.
in the widowed and divorced and see what that gives us if it gives us the right answer. Everybody agree? So not married, you're absolutely right. That's good semantics on that. 51.4 plus 13.6 plus 22.0. Everybody agree?
Sir, yes, sir.
Okay. What's the total on the numerator?
87.
87?
Yeah.
Okay. Out of 210. What's the decimal rounded to 3 places? Right? Did you get that? 51.4? Is that right? 87 is the sum of the numerator.
Oh, okay.
Then you need to do it out of 210 because they asked for 3 decimal places, not the fraction.
0.414.
And so we divide.
You do, because you need to always pay attention to how they want the answer put in, right? Do they want it as a fraction or do they want it as a decimal? And perfect, good job, nicely done. Does that make sense, everybody?
I feel like we're
So
on
pay really close attention to the wording. Not married doesn't mean never married. Okay, not married means whatever situation you're currently in, you don't happen to be married. Okay, so good job. Let's move on. I'm going to erase this, okay, everybody? Erase this right here. That way we have a little bit of a cleaner slate to work on. Okay, find the probability that the person is widowed or has never married. First and foremost, we need to know the what? The total. That's what everything is out of. So we know we're out of 211.5. And here we go. Widowed or has never married. There it is. We don't count the divorce, right, everybody? So widowed, 14.4. Never married, 52.7. What's the total on the numerator?
67.1.
67.1 out of 211.5. Rounded to 3 decimal places.
0.317.
There it is. Let's go check that. All right, love it. Not bad, right?
Love it here.
Let's take a look at this next one. Okay. Still recording?
Yeah.
Perfect. All right, so find the probability that the person is male given that this person is divorced. Stop for a moment here. What is our total? Is our total 209.6?
No, anyway.
No, it's like the green and blue circles, right? The discs. We aren't using that total. What we've just done is we've pulled all the divorcees, which is this. That's your denominator. Does that make sense, everybody? Okay? Given that a person is divorced, that means you're already looking at the divorce category. Find the probability that the person is male, meaning that you need to look up at the males, and so it's 8.5 out of 20.9. Does that make sense? What's the decimal on that? 0.407. Very important that you pay attention to that, because it's like the disc problem, and there it is. Good job. Okay? Let's take a look at this next one. There we go. Find the probability that the person has never married, okay? Given, boom, important, right there, that this person is a woman. That means you are not looking at this total. Everybody agree? You're looking at what?
111.3.
Exactly. Given that the person is a woman, meaning that you're out of 111.3. You're pulling all the women and now looking at the stats within that. Never married is where? 22.5. Okay? And what's the decimal on that?
0.202.
202.
Oh.
Does that make sense? Good job. And I'm going to not do 27 because it's just like that, and that's for you guys to do. And there you go. Important note that we will probably have our first test. We'll have that test on next week on Wednesday. Okay, for you guys. All right.